Year 13, Chapter 9, Further Differentiation, and links back to Chapter 5, Differentiation. Lesson 5, Applying Our Knowledge. So we're going to have a look at a series of exam questions involving differentiation, using the differentiation techniques that we have recently learnt about. So have a look at the example here. We are asked to find the coordinates of the turning point, P, which means that we need to differentiate. So we know at the turning point the gradient is equal to 0, so we need to find dy by dx. Now, we need to identify what type of function we have here, and we can see that overall we've got a product of two functions. So we're going to make sure that we use the product rule for differentiation. So let's start by setting up u, which is equal to e to the 2x, and then let's set up v, which is equal to cos x, the two parts. We then need to use the chain rule to differentiate e to the 2x, but that's a very easy derivative. Exponential functions stay the same. We multiply by the derivative of the inner function, and the inner function is just 2. Look at how quickly we can apply the quick chain rule. dv by dx is then equal to negative sine x, which we should know. And we can then set up dy by dx using the product rule, as this tells us that we need u dv by dx plus v multiplied by du by dx. So we have all of the component parts we need. Let's put them together. So first of all, u times dv by dx, first of all. So that's e to the 2x multiplied by negative sine x. And then we want to add on v multiplied by du by dx, which gives us 2e to the 2x cos x. Now we know at any turning points, dy by dx is equal to 0. So I'm going to take this derivative that I've just calculated, negative e to the 2x sine x plus 2e to the 2x cos x, and I'm going to set it equal to 0. Now, I'm allowed to divide through by e to the 2x because e to the 2x is not equal to 0 and can never be equal to 0. We know the e function doesn't cross the x-axis, so we can divide through this legitimately. This then leaves me with 2 cos x equals sine x after a little bit of rearranging, and then dividing through by cos x will give us 2 equals sine x over cos x, which of course is the same as tan x. So we're left with solving tan x equals 2. Now we are working with differentiation, calculus, and we're working with a trig function, so we must be in radians for this to actually work correctly. So when we take shift tan or inverse tan on our calculator, arctan, we need to be in radians, and x works out to be 1.1014, which will round 1.11 to 3 SF, and we need to substitute the unrounded value into the original equation. So I recommend saving this in a calculator memory and then substituting it into the equation of the curve. We get 4.0942 ... so y is 4.09 to 3 SF. Example 2, find the exact gradient, so we need to look for dy by dx in a minute, of this curve. Now, identify what type of function it is. It's a composite function, which means we'll need the chain rule, and it's also overall an ln type function. It's ln of something. So we can use the quick chain rule to differentiate. We know that ln functions differentiate to 1 over whatever we are taking ln of, in this case 1 subtract cos 2x. but we must remember that we've got to then multiply by the derivative of the inner function, which requires an application of the quick chain rule. 1 differentiates to 0. Now we know cos differentiates to negative sine, so because there's already a negative there, we'll end up with sine 2x, but of course we need to multiply by the derivative of the inner function here as well, so we get 2 sine 2x. So remember that it actually would have been negative 2 sine 2x, but because of this existing negative here, we end up with negative negative, which becomes positive. So this is our answer, 2 sine 2x over 1 minus cos 2x, but we have to find the exact gradient at the point with an x-coordinate of pi by 6. So look at this, it's already in radians set up ready for us. We need to substitute pi by 6 into the gradient formula here. Another good occasion on which to save this as a memory in your graphical calculator and input the calculation in terms of that memory rather than retyping pi by 6 multiple times. And the answer works out to be 2 root 3. Example 3, we're given a function and we need to find its gradient. Hopefully you can see straight away that it is a product here. We may need to use the quick chain rule as well as part of our differentiation, but we're going to set up for the product rule. So we want to make sure we've got u equal to one part, we'll say e to the negative x, v equal to sine 2x, and let's differentiate both of these. So a bit of quick chain rule here. E to the negative x differentiates to e to the negative x multiplied by the derivative of the inner function, so it's negative 1. So negative e to the negative x. Quick chain rule here again for v, sine 2x differentiates to cos 2x multiplied by the derivative of the inner function, which is 2. Now, what is the product rule again? Let's remind ourselves. So dy by dx is equal to u multiplied by dv by dx plus v multiplied by du by dx. So let's take these parts together. So u multiplied by dv by dx first of all. Now this gives me 2 e to the negative x cos 2x, and then I want to add on v multiplied by du by dx, so that's negative e to the negative x sine 2x, and I'm going to factorise, so take out e to the negative x, and then we have 2 cos 2x minus sine 2x here. Now, hence show that the curve has a stationary point when x is equal to a half arctan 2. Now, there are two techniques we could use. We could substitute the x value into this and show that we get a gradient of 0. I think that would be a more complicated way forward because substituting in an arctan 2, unless we convert it to a decimal, makes things a little bit trickier. So I'm going to say we know at any stationary points dy by dx is equal to 0. So that gives me e to the negative x 2 cos 2x minus sine 2x equals 0. I can divide through by e to the negative x as it can never equal 0. So this leaves me with 2 cos 2x minus sine 2x equals 0. And let's just rearrange this. So dividing through by cos 2x gives me 2 equals sine 2x over cos 2x. And of course, I can use an identity to tell me that means tan 2x is equal to 2. 2x is then equal to arctan of 2, and x is equal to a half arctan of 2, which is what we were required to find in the question. Example 4, we have got to show that this function differentiates to this result here, quite a complex looking derivative. Now it's another product, there are the two separate parts, So we can say that u equals x squared, which of course has a very easy derivative of 2x. And v is going to be this part here, which I will rewrite as 1 plus 4x to the power of a half. dv by dx we can then find. Now, we're going to have to use the quick chain rule. It's a power function. Multiply by the power of a half, reduce that power by 1 to negative a half, and multiply by the derivative of the inner function, which is 4. So this simplifies to 2, 1 plus 4x to the negative a half. What is dy by dx then equal to? Again, we're using the product rule, which we've now seen many, many times. And this should be very, very familiar to us as a process. So, starting by multiplying these parts together, u multiplied by dv by dx, we have 2x squared 1 plus 4x to the negative a half. And then multiplying these parts together, we then have 2x 1 plus 4x to the power of a half. And I'm then going to factorise this. We can take out a 2 and an x, and we can also take out the lower of the two powers here, which of course is 1 plus 4x to the negative a half. So let's do that. So let's take out a 2, let's take out an x, and let's take out 1 plus 4x to the negative a half. So inside my brackets, I've then got to have an x plus 1 plus 4x. Now, why does that work? Because this 1 plus 4x is effectively to the power of 1, and when these two are multiplied together, we add the powers, which would give us an overall power of a half, which is what we want. So, simplifying the content of the large square bracket gives me 5x plus 1. I cast an eye on the final answer that I'm trying to get to, and I can see this matches up with my work very nicely because I have the 2x that I need here. I have the 5x plus 1 in the numerator that I also need, and this part here can be written in the denominator as 1 plus 4x, the square root of. So I get to the required answer. So we have a sketch of a curve which has asymptotes at x equals 0 and x equals a, and we've got to find the value of a. Now, these vertical asymptotes arise when the function ends up with a 0 in the denominator. So what happens if 2x minus x squared equals 0? We get problems. So factorising this, x bracket 2 minus x equals 0. Now that gives us x equals 0, which we know is an asymptote here. And we also get x equals 2, which must be the vertical asymptote over here. So a has got to equal 2 for part 1. So the domain of the function, remember, is the permissible set of x values. So we can see clearly from the graph sketch that we're allowed any x values. The function exists for x values between 0 and a, but not anything equivalent to 0 or a, which we now know is, of course, 2. So the domain is that x can be between 0 and 2, but not equal to either of those two values. Part 2, find dy by dx and show that it's equal to this. Now, there are lots of ways of finding dy by dx. We could use the quotient rule. I am actually going to rewrite f of x as 2x minus x squared to the negative a half, and I am actually going to use the quick chain rule, using the fact that this is in the format of a power function. So I want to multiply by my power of negative a half. The contents of the brackets stay the same. We then reduce the power by 1, so it becomes negative 3 over 2. and we then multiply by the derivative of the inner function here, which is 2 minus 2x. And of course, now I just need to show that this can be expressed in this format here, and I can already start to see some starting points for taking it in that direction. So, first of all, I have a negative 1/2 here, and I have 2 minus 2x. So if I multiply 2 minus 2x by negative 1/2, I'm going to get negative 1 plus x. And then this part here, I can bring that into the denominator, 2x minus x squared to the power of 3 over 2. And that's essentially the final answer. We'll just rewrite it exactly as it is there. Now, the last part of this, find the coordinates of the turning point of the curve and then write down the range of the function. So we know at the turning point, dy by dx must be equal to 0. So if we set the gradient function equal to 0, the only way that this can equal 0, its quotient, is if the numerator is equal to 0, i.e., effectively, you could multiply both sides by the denominator to effectively get rid of it. So we have x minus 1 equals 0, so x is equal to 1. Now, if we substitute x equals 1 into f of x, what do we get? Well, we get a y-coordinate of 1. In theory, it's a square root, so it doesn't include a negative root here, and we can also see that from the diagram. It's clearly a y value of positive 1. Now, write down the range of the function. Range refers to the permissible set of y values of the function. Now, we can see that the lowest possible y value is here, and then after that, the curve exists for all other possible y values. It just carries on going upwards. So the range of this function is simply that we're allowing any y value greater than or equal to 1. Example 6. We're given another curve with an asymptote, and we've got to find the value of x at that asymptote. So we know at the asymptote, the denominator is going to equal 0, which is what causes the break in the graph. It causes the discontinuity. So we know that 3x minus 1 has got to equal 0, which gives us x equals 1/3. So a is equal to 1/3, and the equation of this vertical asymptote here, which I'll highlight in green, is x equals 1/3. Part 2, show that dy by dx is given by this result here. We've got to find the derivative of the function. I'm going to use the quotient rule to do this. It's set up very nicely. We can see the numerator and we can see the denominator functions very clearly. So u equals x squared, du by dx is equal to 2x. That was a simple derivative. V equals 3x minus 1, and dv by dx is equal to 3. Now, do we remember the quotient rule? Tells us that we want v multiplied by du by dx, subtract u multiplied by dv by dx, and then the whole thing has got to be divided by v squared. So let's put all the pieces together. First of all, so we want 2x multiplied by 3x minus 1, subtract 3x squared, and then the whole thing needs to be over v squared, which means over 3x minus 1 all squared. So simplifying this gives us 6x squared minus 2x minus 3x squared all over 3x minus 1 all squared, and this then simplifies down to give us 3x squared minus 2x over 3x minus 1 all squared, which is essentially the final answer after a small amount of factorisation in the numerator. That is part 2, complete. Now, find the exact coordinates of the turning point P. So what do we know about the turning point? Well, we know that at P, dy by dx is equal to 0. So that means I need to set x, 3x minus 2 over 3x minus 1 all squared equals 0. Again, it's a division, it's a quotient. The only way this can equal 0 is if the numerator is 0, which then leads us to two possible values of x equals 0, which means there's a stationary point here, and then at P we can clearly see x equals 2/3. We then need to calculate the y coordinate, so we substitute back into the original equation. So y then equals 4/9. Now, calculate the gradient of the curve when x equals 0.6 and 0.8, and hence verify that P is a minimum point. Now, these two values for part 3 have been chosen because they're either side of the coordinate we've calculated, the x-coordinate we've calculated for P, which is 2/3 or 0.6 recurring. So I always like to set my working out in a neat table so we can see exactly what's going on. We know when x is 2/3 the gradient is 0, but we've been asked to calculate the gradient at 0.6 and 0.8, which, as I've said, are either side of 2/3. This is a great opportunity to again use your calculator carefully and to store these values in a memory, say x, and then substitute them into the gradient formula. Be careful, make sure you're substituting into this result here, the gradient formula, and not the original equation. So when x equals 0.6, dy by dx is negative 0.1875, so it's negative, it's less than 0, which means we have a negative gradient to start off with, then we have a 0 gradient. What happens when x is equal to 0.8? We get a gradient of 2, which is positive, greater than 0. So this shows us, the change in sign of the gradient shows us that P is a minimum point. We must ensure we make some kind of statement explaining what we've done at the end of the question. Example 7, we're looking for a stationary point. So again, we need to find dy by dx, and there's a product here. I'm going to set u equal to x squared, I'm going to set v equal to ln x, and I'm going to differentiate both of these parts of the product, two easy derivatives here. Now, I'm going to set up my product rule again for dy by dx. So let's put everything together. So we've got x squared multiplied by 1 over x, and we've got 2x multiplied by ln x. So this then simplifies to give me x plus 2x ln x. Now, at the stationary point, we know dy by dx is equal to 0. So this then tells me that x plus 2x ln x equals 0. Factorise, 1 plus 2 ln x equals 0. Now, in theory, that gives me x equals 0, but that's not possible because we cannot substitute x equals 0 into this original equation here because we'd have to take ln 0, which is not feasible. So x equals 0, I'm going to say is not feasible as ln 0 does not exist. So we're ruling out that one as an option. The other option, however, is that 1 plus 2 ln x equals 0. So 2 ln x equals negative 1. ln x equals negative 1/2. And then we need to take e to the power of both sides. So we cancel out ln, so we have e to the negative 1/2, But what is that really equivalent to? It's 1 over e to the half, and a power half means square root. So we end up with the correct answer here. So example 8, part 1. What type of function do I have here in part 1? Well, I'm going to rewrite it as 1 plus 2x to the power of a half, and it's a composite function, so I'm going to use the chain rule to differentiate it. It's the format of a power, so multiply by the power of a half, reduce the power by 1, negative a half, multiply by the derivative of this inner function, which is just 2. So this then leaves me with 1 plus 2x to the negative a half. Part 2, we've got to differentiate this function here. Again, it's a composite function. I'm going to use the chain rule, but this time it's an ln style function. So y equals ln 1 minus e to the negative x. We know that ln functions differentiate to 1 over the original inner function, but we need to multiply by the derivative of this. So that means we're going to multiply by, now, negative e to the negative x. There's a negative here, which is part of the question. Put that in there. And then if I'm differentiating e to the negative x, so this inner function here, e functions differentiate to themselves, but we then multiply by the derivative of the inner function here, which of course means we get another negative, because if you differentiate the negative x, you get negative 1. So this then gives me e to the negative x over 1 minus e to the negative x. Now, how do I express the final answer in the correct format here? Well, I'm going to multiply the numerator and the denominator by e to the x, which is a very useful little trick. The numerator then becomes e to the 0 or 1, and then the denominator becomes e to the x minus 1 there. Just remind yourself, e to the x multiplied by e to the negative x, you add the indices, x plus negative x is 0, e to the 0 is 1. So we're given a trigonometric function defined across the domain negative pi to pi, but we're only given the graph for a portion of the domain from 0 to pi. So our first job is to find f of negative x in terms of x. Now, f of negative x means we have sine negative x over 2 minus cos negative x. Now, you can check this using a calculator, or you can think about the graphs, but sine x looks like this. So we can see that sine of negative values is simply the negative sine of the positive value. So sine of negative x is negative sine x. It's a reflection in the x-axis. Now, in the denominator, cos of negative x, well, if we sketch the cosine graph quickly, it looks like this. So you can see that cosine of these negative values gives you the same result as cosine of the positive values, like that. So the denominator will be minus cos x. Cos of negative x is cos x. So two useful pieces of information there. Sine of negative x is negative sine of x. Cos of negative x is simply cos x. So you can hopefully see that this result is simply the original function, but with a negative in front of it. So f of negative x is negative f of x, which of course means a reflection in the x-axis. So if we're sketching the function for the complete domain, then it's going to look as normal like that, but then this part will be a reflection like that. Now, the next part involves differentiating and finding f dash x. So, part 2, the derivative. Now, can you see that this is a quotient function? So, I'm going to say the numerator u is sine x, so du by dx is cos x, and the denominator v is 2 minus cos x. 2 differentiates to 0, cos x differentiates to negative sine x, so we would have negative sine x, which is just sine x in the derivative. So let's set up the quotient rule. So what does this then give us? So v times du by dx then gives me 2 minus cos x multiplied by cos x minus u multiplied by dv by dx, which gives me sine x multiplied by sine x, or sine squared x, which we can write down in a minute. And this is all divided by v squared, which is 2 minus cos x all squared. Now, simplifying all of this gives me 2 cos x minus cos squared x minus sine squared x, all over a denominator in its factorised form, like that. So we have 2 cos x minus cos squared x plus sine squared x, all over 2 minus cos x all squared. Now, of course, that gives me 2 cos x minus 1 over 2 minus cos x all squared. Now, hence find the exact coordinates of the turning point P. So we know that at P, we're looking for dy by dx to equal 0. So that tells us that 2 cos x minus 1 over 2 minus cos x all squared equals 0. As we've come across previously, the only way this can be 0 is if the numerator is 0. So 2 cos x minus 1 equals 0. Cos x is equal to a half. And then if we take arc cos of a half, we know this is going to give us pi by 3. We can then substitute that back into the original equation up at the top, circled in red, to get an exact value for y, and this equals root 3 over 3. Stating the range of the function, remember the function actually looks like this and has rotational symmetry. So this point here, which is pi by 3 root 3 over 3, is matched by this point here, which would be negative pi by 3 negative root 3 over 3. Now, the range refers to the possible y coordinates, so it's clear from the graph that y can run between root 3 over 3 and negative root 3 over 3. Example 10. We're given an exponential curve, and we've got to find the coordinates, first of all, of P for part 1. Now, P is the y-intercept, where x is equal to 0. So y is then equal to e to the 0 over 1 plus e to the 0. E to the 0 is 1, so the y-coordinate is a half. So P has coordinates 0, a half. Part 2, finding dy by dx. I'm going to use the quotient rule to do this. So u is equal to e to the 2x. Differentiating that, bit of quick chain rule here. We get 2e to the 2x, and v, the denominator, is 1 plus e to the 2x, and actually that will differentiate to 2e to the 2x as well. Let's set up the quotient rule. So this then gives us 1 plus e to the 2x multiplied by 2e to the 2x, and then we subtract from that e to the 2x multiplied by 2e to the 2x. And we ensure that the whole thing is over a denominator of v squared, which is 1 plus e to the 2x all squared. Let's expand the numerator. So we have 2e to the 2x plus 2e to the 4x minus 2e to the 4x. And this has a final simplification in the numerator because these parts cancel out. 2e to the 2x over 1 plus e to the 2x all squared. Now, hence find the gradient of the curve at P. So at P we know x is equal to 0, so dy by dx is then equal to 2e to the 0 over 1 plus e to the 0 squared, so that is 2 over 2 squared, which gives us a half, and that's the gradient at P.